Thank you for joining us for this DDi CADcast. Today's topic is What's New 2015 SolidWorks Simulation. In SolidWorks Simulation 2015, we can now create a bonded contact between non-touching edges of shell bodies. Here's an example where we take two surface bodies with a small gap in between. We then can apply a bonded edge-to-edge contact between the two, run the study, and see some displacements. As a comparison, I've ran a separate study where there's no gap, so we can compare some results. Although the results are very comparable in this case, we must understand that when we use a bonded edge-to-edge contact with a gap, the bonding formulation is an incompatible mesh. In other words, nodes of the shell edges participating in the bond are not merged. Also new in 2015 is a capability that we've all been waiting for. That is the ability to self-detect faces of a body that come into contact with themselves. Now this involves springs or brackets, any kind of geometry that needs to bend and potentially come into contact with itself. Previously you had to go in and use split lines to segregate surfaces and then add the proper constraints so that the software understands that these are two separate surfaces colliding into each other. And in 2015, that is no longer the case. We can use a simple no penetration contact set. Select the self-colliding face and choose self-contact as an option. Now this constraint is not automatic. You need to turn on the option self-contact to enable it. Reason being is that it's very calculation intensive and you don't want to have it turned on unless you really need to go through that calculation. Another note about the self-contact constraint is that it's not available for 2D simplification. Next, let's talk about some new capabilities that have been added to fatigue studies. In 2015, we can now predict the life and damage plots using fatigue studies based off of our harmonic studies or a random vibration study. Now this is a two-step process. Let's do an example here with this particular little motor mount. You first have to enable and create a harmonic analysis. Make sure it runs properly, maybe do a little interrogation. Maybe let's figure out here what frequency or mode gives us the highest displacement. About 56 hertz. Now that we have some data from this harmonic analysis, we can create a new fatigue study. Now the important part here is to specify what flavor fatigue study to go with. We're going with the harmonic fatigue study. Let's go ahead and create a new event, just like before with fatigue analysis. This time we're going to specify our specific dynamic harmonic analysis. We can enter the frequency that we'd like to load this thing with. We said earlier 56 hertz was the value of interest there. And just like before, we can enter the number of cycles and the scale factor. Next, we can verify our fatigue data, and that remains unchanged. And let's run the study. Once we run the study, we can now interrogate and see a damage plot and a life plot based off of that harmonic study. The same workflow applies if you're doing a random vibration and you want to figure out the fatigue from a random vibration study. Simply go in, step through the random vibration study as normal, create a brand new fatigue study, specifying the random vibration flavor, add your event, and apply or edit your fatigue data. Now with a random vibration fatigue analysis, you're going to have to enter your two SN Basquin curve constants, or you can estimate the Basquin constants from the SN curve. Now, if you had more than one event to fatigue analyses, multiple fatigue events added will assume to be sequential, and there will be no interaction between the two events, or 2+ events. Next, let's talk about frequency. In 2015, we've added 3 additional frequency analysis graphs to our studies, for frequency and for our dynamic studies. We can see that we've added a frequency versus mode number plot, frequency versus effective mass participation factor, and lastly, frequency versus cumulative effective mass participation factor, which when doing dynamic studies, it's always important to determine the exact mass participation of your models in the direction of agitation to get confident results. Plotting these frequency versus mass participation factor plots helps you capture the trends and to see if you're plateauing on your mass participation factors. For example, down below here, you can see that we're plateauing here at about 90 to about 97% mass participation factor cumulatively. To access these plots, you simply run your study, or at least your frequency analysis, right-click on the results folder, and choose Define Frequency Response Graph. And this will allow us to choose the flavor response graph or frequency analysis graph we want to display. So we can see which mode perhaps has the most mass participation. And perhaps here we can grab a trend to give us some confidence in the number of modes we've chosen for our analysis. Again, these flavor graphs are available for our frequency studies and for our linear dynamic studies. The next capability we're going to be talking about is called the Load Case Manager. Now, as you can see here, this functionality is currently only being used in static studies. Hopefully in future releases we'll be able to see this functionality in other study types. But the idea behind this is similar to design studies, where you can take combinations of constraints, whether it be fixtures or displacements, loads, and combine them in different combinations and get some results. Now, the idea behind this is that it's very local to one particular study. It has a very nice interface. Let's take a look here in SolidWorks, and we'll step through the UI. Now, to initiate this, you would have to start a new static study. Typically, you want to go through and do all of your setup, whether it be fixtures, adding connections, materials, forces, etc. Do a right-click at the very top of your study tree and choose Load Case Manager. Now, we've partially completed one here to show and save some time, so I'm going to go in and turn on my Case Manager and step through this here with you. Now, the way it's set up, at the very top row, we have our combinations of connections, fixtures, forces, connectors, etc. And for each row, we can enter a new load scenario. For example, we currently haven't used torque, so let's add a scenario where we only look at torque as a load. I'm going to go ahead and label my scenario or load case. I'm going to make sure that my stabilizing constraints are all turned on, and for my loads, I'm going to make sure that only my torque load is turned on and unsuppressed. Now you can add as many of these load cases as you would like in this section. Next, down below, we have load case combination. Now, to add a load case combination, just simply click on the cell, and we can go ahead and remove what's in there and add our own combination. Perhaps we want to do lateral plus maybe torque. Click OK, and there's next combination. As far as results, you need to set up a sensor. This is very similar again to design studies, where you go in and you add your sensor. It's going to open your Add Sensor Property Manager, and then you choose your sensors. Those are going to get populated in the bottom section. Once you're done setting up your Load Case Manager, you can simply hit Run. The software will calculate all your scenarios, and we can interrogate results. Now we're presented with the Results View tab, and we can step through all the different results based off of the load cases. Now, before we move on to the next topic, I want to mention something that's new in 2015 related to materials. In 2015, we now have access to our own little favorites folder or favorites list, just like we do have inside of regular SolidWorks CAD. Just simply right-click over the solid body, and now we can go in and choose our material from our favorites list. As far as managing your favorites list, just simply go into the materials database and select manage favorites. Another enhancement in simulation in 2015 is the change in the user interface for applying forces, pressures, torques to your studies. In any load type where you were able to go in and turn on non-uniform distribution, we now have support for cylindrical and spherical coordinates in your equations. All right, let's continue our conversation with talk about the mesh and some new mesh abilities with 2015. So whenever you go in and you're having trouble meshing a certain body, the mesh failure diagnostics tool has been key in helping to proceed with resolving your issues with the mesh. In 2015, we've added 2 additional options to help with your meshing problems in your simulation studies. Let's take a look at this example. Let's go ahead and try and mesh the model. So we have a problem with one particular part. Let's click on the mesh failure diagnostic. And over to my right, you're going to notice we have 2 additional entries. We have show bodies which fail to mesh, and a specific show mesh for all bodies, which is similar to what you are used to seeing in 2014 and previous. So not only do you have the name of the part, the surface or the geometry that was related to the mesh failure, but now you can go in and isolate the components in your graphics area. Our next topic involves nonlinear studies. 2 very exciting capabilities have reached nonlinear studies. The first one is intermediate results. Now, the way this works is we start with a nonlinear study, and actually before going into the nonlinear study, there's an option that you want to make sure you enable in simulation for this to work. Let's go into simulation options, and under default options, let's click on the results category. And at the very bottom of our results category, make sure that you checkbox show intermediate results up to current iteration when running. Now, only after this option is turned on will you be able to see your intermediate results on any new nonlinear studies after that point. So here we have a study, and let's go ahead and hit run so we can take a look at how that runs and looks. So the importance of this is we can see the development of our results. Before, we had to wait until we reached 100% to look at results and then readjust our constraints, reevaluate our setup. Now we can go in, and as soon as we see some intermediate results, we can see where our study is going, and we can stop the study prematurely, adjust, hit run again without having to wait the full 100%. Again, saving potentially an immense amount of time when running your nonlinear studies. The other enhancement to nonlinear studies is the inclusion of cyclic symmetry in our studies. Here we have a portion of this little brake assembly. And under fixtures, under advanced fixtures, we now have the ability to use cyclic symmetry. This has previously been run, and we can take a look at and reap all the benefits of using symmetry in our nonlinear studies. Now, just like in our other study types, when using cyclic symmetry, you have to make sure that your angle that you've used to cut your model is evenly divisible into 360 degrees. Now, in the area of performance, there are a couple of items that are worth mentioning. The first one is a new solver type in simulation. The new solver type is called the Intel Direct Sparse Solver, and it's available for static, thermal, frequency, linear dynamic, and nonlinear studies. Now, the idea behind this new solver type is that it's more efficient at memory allocation algorithms and using the multi-core processing capabilities of our Intel chipsets when solving calculations. So if you have an Intel CPU, you may want to try running the Intel Direct Sparse Solver. Another item worth mentioning related to performance and efficiency is the decreased processing time when running simulation studies. In 2015, they're reporting a significant decreased time when you're running your solver. You have your solver window and you see when it says processing. This is especially true when you're working with shell bodies and you're having to resolve thicknesses and orientations and contacts. Also, they're reporting a decreased processing time when detecting bonded or no penetration contact sets as well. Another change in 2015 is related to the user interface. We now finally have a ability to run specified studies, meaning we no longer have to go in and say run all studies and then bite the bullet on the ones we didn't want to run. We can go in and by hitting the pull down under run this study, we can now checkbox the specific studies that we would like to run. Now in the run specified studies box, you can go in and again checkbox the columns you'd like to run or mesh only. Also, you can see the configuration, name, and conveniently the mesh status. And you have that really convenient notes section towards the end. Now, an interesting feature about this capability is if you hit run for a study that's dependent on a parent study, for example, like a submodeling study or a pressure vessel study, the program will also run that parent study first, then it will run the child study. Next, let's talk about shell elements with simulation. In 2015, there's a new user interface that allows us to edit, organize, visualize, and even define all shell elements in our studies. So we've created a frequency study, and to invoke the shell manager, we'll go up to the simulation dropdown, shells, shell manager. We could also go in and right click if you have an existing shell element or shell body. You could right click over the element and say shell manager as well. Now, not only does it have the shell manager property manager, so we can define shells by selected surfaces. If we have a solid, we can do that with this interface, but importantly down below we have the actual shell manager area. Which will take and itemize every single surface body and allow us to enter the material type, the model type, thin or thick, the actual thickness, the units, the material associated to the body, the offset, those traditional offsets, the bottom, top, middle, and the ratio that we're all used to in previous releases of simulation, and the actual shell name. The reason behind the shell manager, again, is to organize your shell elements in one consolidated area. For example, we have a column here called groups. For example, we can take this base lateral group, and whenever we change an item in that group, hit enter, it's going to give us feedback. Group properties are modified. Once we click OK, it's going to change that item, in this case thickness, for every shell body that's tagged to that group. Now we can choose to include or exclude any other shell items by hitting the pull down and choosing the actual group, or we can also create a new group by clicking on Manage Groups, entering a new name. We can add a new group, or we can take and mass edit the different properties involved for each group. Lastly, we can visualize our shell bodies in two ways. One way is by the thickness of each shell element. We can turn on the legend, or by the material type. Lastly, we can visualize the preview for all our shell bodies. Or for selected bodies, which is what we are familiar with in early releases of simulation. whereas the convention is, again, green is the top and orange is the bottom. The last enhancement for Simulation 2015 is that we now have simulation results for the colorblind. For any of our result plots that involve color, we simply go in and right-click on the result plot, go to color, or we go to chart options, scroll down and expand color options, and under the pull down choose optimize for color blindness. And again, this color scale is optimized specifically for red-green colorblind users. And this ability is available for all versions of Simulation. So that sums up the topics for 2015 SolidWorks Simulation What's New. For more CADcast topics, please check out our YouTube channel at www.youtube.com/DDiCAD or our tech blog at DDi CAD.com/techcenter. Thanks for watching.